Hello everyone, welcome back to introductory course on computational fluid dynamics. So in last session we discussed about conservation and non-conservation form of equation or conservative and non-conservative form of equations which we come across in CFD. We discussed about the definitions and difference between each of them and their impact on solution. So today we are going to start with forms of equations which are suitable for CFD. So this is the outline of the today's session, which is what are the different forms of equations, how we are going to form that, and how we are going to use them to solve. Then we have shock fitting and shock capturing, which are the two approaches to solve supersonic flow over bodies which involve formation of shock wave. Moving forward, so consider continuity equation. This is the continuity equation in partial differential form. Now, if I expand this divergence term, I can write it as dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w with dou rho by dou t equals to 0. So how did we end up at this conclusion? Nabla is equals to dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap. So when I multiply with rho into u I cap plus v j cap plus w k cap, which is the velocity, rho into velocity, so the dot product of these two will end up with this kind of expression. Divergence of rho v can be written as this. So ultimately your equation will be reduced to something like this, which is dou rho by dou t plus this equals to 0. Dou rho by dou t plus your divergence of v is equals to 0. Okay, so that is what you can note down, the equation, which is dou rho by dou t plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w is equals to 0. Now similarly, let us consider momentum equation. So momentum equation in x direction is given by dou by dou t of rho u plus divergence of rho u v equals to minus dou p by dou x plus dou tau xx by dou x, dou tau yx by dou y, dou tau zx by dou z plus rho fx, where fx is the body force and tau are the shear terms and p is the pressure. Similarly, let us consider all the components, that is x, y and z components. All three components can be written in this form, which all the derivations we have already done in the previous sessions. So you can refer to those for these kind of equations. So these are the x, y and z components of momentum equation. Similarly, let us consider energy equation. So energy equation, as you can see, dou by dou t of rho into e plus v square by 2 plus divergence of rho into e plus v square by 2 into v. So same thing I can expand, similar to what we have done in the earlier case, where now I'll end up with divergence of rho e plus v square. So I'll write e rho e plus v square by 2 dou by dou x into u plus dou by dou y into rho e plus v square by 2 into v plus dou by dou z into rho E plus V square by 2 into W. So this is nothing but divergence of rho E plus V square by 2 into V. So this is the equation which you can assume. Now you see dou by dou t into rho plus E square, rho into E plus V square by 2, and the divergence terms you can see 1, 2, 3 terms are there. Similarly, rho q dot, dou by dou x of k, dou t by dou x, dou by dou y of k, dou t by dou y, which are the terms which are nothing but the conduction equation, and these are the rate of work done due to pressure and shear. So now if you observe all these equations whichever we have discussed now, we want to unite them or combine them into one single equation or one single set of equation. So that is the form of equation what we are trying to look at. So this is the form where I want to convert all these three equations in such a way that I'll end up with one single equation which define all the consideration. That is, I can combine continuity equation, momentum equation and energy equation into one single set of equation, and if I solve that one set of equation, then I can end up with the solution. So this is what the form of equation which is suitable for CFD. So let us try to combine them. So to combine, let us consider continuity equation and momentum equation. I am taking example of only these two because this will act as a reference for us. Continuity and momentum. Now you see x, y, z. Now just look at this. It has all the components here, which are with respect to t. Similarly, separate the components which are having partial differential with respect to x. Partial differential with respect to y. Partial differential with respect to y. X and y. Right? So if we try to streamline them into one single equation where I can rewrite them. So what I'll do, I'll try to separate them in form of the terms which are divided by or which are partially differentiated with respect to time, or which are partially differentiated with respect to x, and which are partially differentiated with respect to y and z respectively. So now I can rewrite them as rho. Now if you go back, here you can see only rho, dou rho by dou t, and in the x momentum rho u, rho v in y momentum, rho w in z momentum. So if you observe this, now if you observe the equation here in this case, so this is nothing but continuity equation. This is from continuity. These three are from momentum equations, and this is from energy equation. So closely observe. These are nothing but dou rho by dou t, dou rho u by dou t, dou rho v by dou t, dou rho w by dou t. So if we segregate them in such a way that now I can say I am writing U as a column matrix which has all these terms. Now similarly, I will take dou by dou x. F represents terms under dou by dou x. So if you see continuity equation again, let's move back to continuity and momentum equation. That will help me out to understand this. Now see, dou by dou x, first term rho u from continuity equation, then dou by dou x p, that is minus p, dou by dou x tau xx from the x momentum equation. So I am not considering y momentum or any other, because everything is with respect to x. So from x momentum, it is going to be minus p and tau xx. Similarly, now if you observe y momentum, you can see dou tau xx by dou x. Then you have dou tau xz by dou z. So 3 terms, 1, 2, 3, 4 terms to be included in the components. Now let's see in this. So rho u, this represents divergence of rho u u. So here u is the component, so you are not going to discuss with that. So your LHS was having divergence of rho u, so I can write it as divergence of rho u into v as u rho u plus rho u v plus rho u w. This is dou by dou x, this is dou by dou y, and this is dou by dou z, because we are going to consider only this as the variable velocity. So rho u is nothing but rho u square. So on the left hand side you had this rho u square, right hand side you have p and tau. So when you bring everything to the next step, minus p will become p, and tau, which was plus xx plus tau xs, will become negative. So we are trying to equate into the source terms. So we'll come across what are source terms and all. For timing, let us understand that this is nothing but the equation. So similarly for x component, you have in y momentum, you have rho u v, which is again divergence term with respect to v, and tau xy. Similarly rho wu minus tau xz, which is again the diverse term from left hand side, and tau xz is the right hand side. If you send this side, you are getting minus tau xz. Similarly energy equation. So energy is equation, you have u tau xx, v tau xy, w tau xz, and dou tau by dou x is the transfer term, and pu is the pressure, and rho e plus v square by 2 is the divergence term on the left hand side from the energy equations. Now hope you understood. So similarly, if we go for with respect to y, this is with respect to time, this is with respect to x axis or x coordinate. Now similarly, if you go for y and z, you will end up with this kind of equations. You can see rho v is the dou rho v in continuity equation, dou rho v by dou y. Similarly, the divergence term, dou rho v by dou y minus tau xs. This is a pressure term. So x momentum, y momentum, and z momentum. This is continuity equation. These three are momentum equation. This is from energy equation. Again, continuity, momentum, and energy equation. So here we have formed into different categories, all with respect to their partial differential terms. For example, u was with respect to time, f was with respect to x, and g with respect to y, h with respect to z. Now apart from these terms, we are left out with another set of terms which we did not come across, which are nothing but, if you observe, rho fx did not appear anywhere in the equation. Rho fy did not appear in any of the equations, did not apply or did not appear in any of the equation. Now similarly, if you go to energy equation, so there are terms which are not considered or not considered into these forms of equation. Let us look into those terms. Those terms are given as j. In continuity, RHS was 0, rho fx, rho fy, rho z from momentum equation, and from energy equation, these are the terms which we did not come across. So these are again body force into or work done by the body force, and this is the rate at which heat added. Rate at which heat added. So these are the terminologies which are left out, and we are going to call them as the source term. Okay, we'll discuss what are the source terms. So these are nothing but these are independent of any of the variables. Like you are not these are not differential terms, rather they are the values. So now if I write all those equations, you can see dou u by dou t, dou f by dou x, dou g by dou y, dou h by dou z. If I combine all those, that should be equals to the right hand side, which is j. So now if you observe, I had 3 equations. Out of those 3 also, let's say continuity, momentum, energy equation, and each of them were divided into different components like x, y and z. Now what I have done, I have converted them into one single set of equation where all the parameters are considered or taken into account, whether it is continuity equation, momentum equation or energy equation. All the equations are brought under one single equation. These are called as forms of equations suitable for CFD, because they account for all the laws, that is continuity, momentum and energy. So mass conservation, momentum conservation and energy conservation are considered into this, and the final expression is this, where each of them, I think we have defined already what is each of them represents. So now FGH are called flux terms. You can see that they are derived from the divergence terms. FGH are divergence terms. So divergence of FGH. Now I can define something like divergence of K, where K equals to Fi plus Gj plus Hk. Then I am going to end up with something like this form of equation. So this is what your reduced form of equation will look like, where it has taken into account all the terms. So FGH are called flux terms, and U is called solution term, and J is called source term. So we want to try to find the solution for this based upon the disturbance created because of the source terms, or based upon the values of the source term, I want to find out the values of U. So we always end up with time marching solutions for these kind of problems. So everything is now can be solved, and all the changes are taken into account in this form of equation. Now let us try to apply it for, as I said, for time marching solution or time dependent solutions. You can directly go for dou u by dou t equals to j minus dou f by dou x minus dou g by dou y minus dou h by dou z. So you will end up with all the time marching solution. Now if I apply to a specific case, let's say where the viscous terms are 0, that means all the tau terms are equal 0, whether it is tau xx, tau xy, all the tau terms are equated to 0. Now for steady flow, dou by dou t is always 0. For steady, anything with respect to dou by dou t will become 0, because there are no changes with the time period. So u are also equated to 0, that is dou u by dou t terms are equated to 0. Then you have j, which is equated to 0, that is heat addition, body force. If we consider everything to be 0, then your j is also 0. So we are not considering heat addition. It's something like a adiabatic process. In adiabatic process, the heat addition or heat transfer is 0. So in those cases, even your j will become 0. Then you will end up with only terms like dou f by dou x equals to minus dou g by dou y minus dou h by dou z. So your reduced form of equation, you can directly find the solution for f, which is dependent on other two values. So if I want, I can rewrite it as dou g by dou y is equals to minus dou f by dou x minus dou h by dou z. Even this is possible depending on the required solution. So depending on the nature of the problem. So here we are considering the solution matrix, solution parameter to be f. So we can consider solution to be dou f by dou x equals to minus dou g by dou y minus dou h by dou z. When I consider this as the dependent variable, these two will become independent variables, or vice versa. When I consider dou g by dou y as dependent, then dou f and dou h will become dependent variable. So this is about the forms of equation which are suited for CFD. So what we have done is we are considered three governing equations, that is continuity, momentum and energy equation. Then we try to rewrite them in form of a single equation which considers, or which can be rewritten in form of all the terms included a simple equation. Then as we reduced that equation for a specific case. For example, in viscid flow, I said tau will become 0. So the equations are reduced there. You are left out only with pressure terms. Now if I say there are no body forces, then your source, no body force and heat addition, then your source matrix has become 0. So you end up with a reduced form of equation which gives you only the time marching solution for spatial coordinate system. Now let us move on to next topic, which is shock capturing. So we know that any supersonic flow you take, there will be formation of shock waves. So this shock wave is nothing but the discontinuity in the flow field. So across the shock wave, the flow parameters will change drastically. For example, you take pressure, density, velocity and temperature. These values or the variables will have entirely different values across the shock wave. There is a sudden change in these properties across the shock wave. So this continuity or discontinuity in the flow must be captured and analyzed for specific cases. So shock fitting or shock capturing, these are the two techniques which we come across. So coming to shock capturing, so it uses numerical techniques which directly allow you to capture the shock wave on a predefined numerical scheme. That means you create a grid over the body. Let's say I have a supersonic nose cone. I create a grid over this. And based upon the solution carried out, I can capture a shock wave like this. So this type of technique we call it as shock capturing technique. So it uses existing methods to calculate the flow characteristics. Directly it uses the governing equation, to be precise. It directly employs governing equations to solve. Now this is the simple example where you have a body and see the shock, and you can see that is a grid or mesh. Grid or mesh. So you can see this grid or mesh. So you are directly capturing the shock wave inside this mesh. Now this technique, as I said, will directly capture the shock explicitly and does not require any tracking of shock wave. It doesn't bother about the formation of shock wave and how the changes are happening with respect to shock wave formation and all. So it need not to concentrate on the formation of the shock wave. Rather, it calculates the characteristics over the complete domain without bothering about the formation of the shock wave. But the calculation, whatever are carried out, will represent the formation of this shock wave. So it doesn't exactly concentrate on the shock formation or location of shock formation. Rather, it keeps on solving the domain where it starts calculating from here, and wherever there is a possibility of shock wave, suppose at this grid point, the calculations are carried out. Based upon that, the shock wave is captured if it suits the calculation procedure or the numerical process. Then, so as I said, shock waves appear naturally, so it doesn't bother about the shock formation. Rather, it calculates the domain. So because of that, it need not to bother about formation of shock waves. Then it uses high resolution finite volume method or finite difference method to solve the domain. So we know the finite difference method and finite volume methods are discussed in the further chapters. So it uses these kind of approaches to solve. So it introduces artificial viscosity so that you get a better solution. Now if you observe the graph here, the image here, the shock is moving from here, but the shock is not having contact with the grid points. For example, you take this grid point. For example, you consider this grid point. This grid point is not coinciding with the shock wave. But whatever we understood in the earlier sessions, that all the numerical calculations are carried out in CFD will be carried out at these specific points called grid points. But the shock at this grid point is not forming, rather it is moving slightly away from the grid point. So to get a better solution, you need to have this artificial viscosity to be included and flux limiters to be included into the scheme so that you can get the solution. Next comes the shock fitting. So this shock fitting requires explicit tracking of the shock wave. That means unlike previous case where you had the domain, you discretized it, then you calculated for the flow process or flow problem. Rather now you don't have this domain, rather you have the body here, you have the body, and based on the formation of the shock wave, you are going to generate the grid or mesh. So to do that, you need to first understand the formation of the shock wave and understand the nature of the shock wave, how and at what location it is going to be forming. So based on the formation of the shock wave, it will develop the boundary layers. This shock wave will become one boundary layer and the body itself will become another boundary to the computational domain. It will ignore rest of the domain, unlike the previous case. In previous case, it has considered complete domain and calculated for all the domain. Now what happens is, it considers only the object and the flow condition. Based upon the flow condition, it will first predict the shock wave formation, the nature of the shock wave and location. Based upon that, it will now decide the boundaries of the domain. For example, you just check this. So this is the object. This is the object which we are speaking of. It's a conical section. Now what it has done is, it has first created the shock wave. You can observe this. This is a shock wave. And using the shock wave, now you can see that there is no grid beyond this shock wave. There are no grids or no mesh generated beyond the shock wave. So this shock fitting specifically speaks of or specifically uses shock wave as the boundary layer or boundary condition. It's boundary condition, not boundary layer. It considered this shock wave as the boundary for the computational aspect. Now the question arises, how does this shock wave is captured, or how this shock wave is calculated? So for the calculation of shock wave, it uses special techniques such as Rankine-Hugnoid equation, which purely deals with the thermodynamic variables. Rankine-Hugnoid equation is purely in form of thermodynamic variables, that is pressure, density, right? So because of that, there is additional equation added. So using that equation, the shock is first calculated. Then based upon the appearance of shock wave, the boundary for the computational domain is set. That is, shock wave will be one boundary and the body of the object itself will become another boundary, and all the computations are calculated. Then behind this or in between these boundaries, the computation is carried out by other governing equations like continuity, momentum and energy equation, whatever we came across in earlier stages. So here shock location is treated as a boundary layer, as I mentioned, not with the mesh cells. So cells are created inside this shock wave, and we are not going to go beyond that shock wave. So this is certain differences between shock capturing and shock fitting. So first one, concept, as I said, explicit tracks of shock wave is not required, but here in shock fitting it is required because it purely depends on the shock wave, whereas in shock capture it directly computes, so no need of explicitly tracking the shock wave. Then boundary conditions require specialized boundary conditions. As I mentioned, the shock itself will become boundary for the flow or for computational domain, so it requires special boundary conditions upfront of the shock wave. Since it is capturing, it requires the conventional boundary conditions which we come across in the general solution of a problem. Now, if you observe, in shock fitting, shock wave is treated as a moving internal body. So we have to consider shock as a body itself, which becomes the boundary of our solution. That is the reason we are considering it as a internal boundary. Now, in this case, these governing equations are directly solved using conservative forms of equation for entire domain. So here the domain is restricted by the formation of shock wave. Next, we use Rankine-Hugnoid equations, and the mesh often aligns within the shock surface. Here shock waves appear steep but smeared due to gradient in solution. So just now just when we were discussing about shock capturing, I mentioned about the formation of shock wave and the grid point. So slight deviation is there. So the shock wave may not pass exactly from the grid point, or it may be slightly deviated from the grid point. So you cannot capture the exact solution, rather you have a rough estimation in case of shock capturing. Then we have accuracy, or very high accurate when we are using shock fitting, and just now I said due to smearing effect the accuracy will be slightly less when compared to shock fitting. So algorithm is very simple in case of shock capturing. It's simple and simple to implement since it is directly aligned with the domain. But when it comes to shock capturing, the algorithms are complex because we have to predict the formation of shock. So we require sophisticated grid management technique. So sometimes we may use something called as adaptive grid generation, which changes with respect to the solution. So it's something like wherever you have more changes in the flow characteristics, there more number of cells are accumulated. Whereas wherever there are less changes or less less variations in parameters, then the mesh size can be larger or coarse mesh can be formed. So adaptive mesh is a technique which we will be discussing in later parts, but it signifies that if there is a shock formation here, then the number of cells here will be increased. Number of cells will increase drastically. Because of that increase in number of cells, the accuracy of solution will always be high, because wherever there are cells not required. If you see shock capturing technique, cells are distributed evenly all over the domain. So because of that, what happens is it has to calculate at all the points, so which slightly increases the computational effort in the for the complex problems. Now if you observe, it can be implemented on any unstructured grid also, but this requires adaptive grids. Shock fitting, it requires adaptive grids which are very much suitable and which increases the accuracy of the solution. Though it is slightly on difficult note, but the accuracy with which you are going to capture the shock and you are going to evaluate the shock will be very high in case of shock fitting. Robustness, shock fitting can be less robust because of rapidly changes in shock formation and adaptive grid generation. So if shock tracking parameters are not defined properly, then you might have very poor result, and so that you have to first initialize and check the shock tracking parameters using the Rankine-Hugenoit equation. So since it is very simple to apply, it is very much robust and it can handle complex geometries or complex flow fields, whereas shock fitting cannot accommodate for complex flow fields which have multiple shock waves or interaction of shock waves with boundary layers. Those kind of things cannot be applicable for, or they are applicable but they are difficult to handle with shock fitting technique. Now computational cost is expensive because the algorithm itself is very difficult to generate, and one more important thing is that the number of computations which are carried out in shock fitting is very high when compared to shock capturing, because shock capturing uses simpler domain, simpler scheme, so because of that it will be very much less. But in case of usage of higher order schemes, then the cost for shock capturing can go little bit high, but even then it is somewhat less than the computational cost for shock fitting. So applications, as I just mentioned, it is very much limited. Shock fitting is very much limited to simpler problems where we have well defined shock wave formation, like straight away you are going to get the shock wave. Then in that case it is very easy or very much useful. But when we go for complex phenomena like shock interaction, shock boundary layer interactions, in those cases shock capturing has a higher advantage when compared to shock fitting. Though the accuracy is a little bit compromised, but it can capture all the phenomena right away using shock fitting and shock capturing. So shock capturing is very much advantage when you have even complex problems, but shock fitting is very much limited to simpler problems which are having a decent accuracy. So that's it for today. So today we have discussed about governing equations which are suitable for CFD. We ended up with certain scenarios, how to reduce that general form of governing equation into a specific case. Then we discussed about shock fitting, shock capturing, and the difference between shock fitting and shock capture. Thank you.